Okay.
Um, so, in today's talk, I will try to explain local interpretable model agnostic explanation, that is LIME. So, LIME is a library which tries to provide the explanation that particular for predictions that particular machine learning algorithm has produced. So basically, it helps in understanding, say, why did the model do a particular prediction or why not something else, and when actually it succeed. Like sometimes it is not successful, and then we don't know. So in these things, it actually helps to have the explanation behind those predictions.
What is XAI?
XAI is explainable AI.
Okay.
So we will quickly go through a video which explains what is Lime and what it does and why what is the motivation.
Sometimes you don't know if you can trust a machine learning prediction. Take a doctor, for example. They cannot trust a diagnosis just because a computer said so. You also need to know if you can trust the model before putting it into production. Let's say we have a machine learning system that can detect wolves. We can look at accuracy and at some of the predictions and maybe look good, but is that enough for us to really trust the machine learning system? What if you could understand why any classifier is making a prediction? Even incredibly complicated models, such as neural networks, random forests, or SVMs with any kernel. Wouldn't that be cool? It's easier to trust a prediction if we can understand the reasons behind it. Going back to our doctor, if the model told him which symptoms are important, he would trust it. It's also easier to figure out if we shouldn't trust the model. If our wolf detection system is actually just detecting snow in the background, we will not trust it, even if the accuracy is high. I said it would be pretty cool if we could understand any classifier. With Lime, we can. Lime is short for Local Interpretable Model Agnostic Explanation. Let's look at this acronym from the bottom up. We know what explanations are. By model agnostic, we mean that Lime treats the model as a black box so that it works for any model. Interpretable means that the explanation produced by Lime is simple enough for a human to understand. Finally, local refers to how we get these explanations. Lime approximates the black box model locally in the neighborhood of a prediction being explained. With Lime, we can explain why a random forest thinks this email is about atheism. It picks up on words such as atheism or God with lowercase g. It also thinks that God with uppercase G is evidence for Christianity. Or why Google's Inception neural network thinks this image is a guitar or a Labrador. In our experiments, we show that these explanations help real users do all sorts of things, such as choosing between competing models, detecting and improving untrustworthy models, getting insights into the model. Lime helps you finally answer the question, why should I trust you? Thanks for watching. Make sure to check out our paper and open source release. It includes the complete source code and IPython notebook tutorial.
Um, so desired explainer characteristics, as we already saw, is interpretability and model agnosticity. So it should not be dependent on the algorithm we are using. And like suppose the model is trained on word embeddings, then we cannot have the word embeddings in explanation. So it should be interpretable. Then another important property is local fidelity. Uh, so what it means is, suppose we are explaining a particular instance, then that explanation should be faithful. Like what it means is, so at least for the similar set of instances, the explanation kind of should be similar. It should not be very different for similar instances. That's what it has one of that meaning. So local fidelity is also an important characteristic. Uh, so we will take a look at some important steps in next few slides in the line algorithm. So first one is interpretable data representation. So basically, suppose you are using word embedding to train a model, but you cannot have the word embedding based explanation. So you need to have some interpretable representation of features. So in case of text classification, what they do is they use binary vector indicating the presence or absence of bag of words. So suppose we are considering a bag of unigrams as features, then it will be just a binary vector indicating the presence or absence of a particular word for that instance. In case of image classification, what they do is they again take a binary vector indicating the presence or absence of contiguous patch of similar pixel, which they call it as a superpixel. So here also, what they do is, let's say in the data set there are 5 kinds of, like say 5 images. So they will just identify contiguous patch of similar pixels in each image and form a dictionary out of it. Let's say we have such 120 kind of contiguous patches, and then that 120 become a feature number of features for a actual model, which we will be explaining. And, uh, and explanation model, which will actually extract the explanation, will have a binary vector which will just indicate which features out of those 120 features are present or absent. uh, so this is how they make it may make the feature space interpretable, so as to have the explanation interpretable. Then another important step in algorithm is fidelity interpretability trade-off. So if the so in order to have the explanation interpretable, we cannot have lots of features in the explanation. So, and if the number of features are less, then the explanation model may be less, can be less faithful. So in order to be faithful, we should incorporate as many features as possible, but in order to be interpretable, the number of features should be less. So they have a function which they try to minimize, which is a summation of uh, loss loss function, which depends upon f. F is the actual model. G is the explanation model, which will derive the explanations. Pi x is the similarity kernel, which we will understand in some time. And this omega g is the complexity of the explanation model. So basically, we want complexity of explanation model low, and we also want this loss function to be as minimal as possible. So this loss function is like a measure of how faithful, uh, how unfaithful the model is, the explanation model. So we want it to be more faithful. And a third step in the algorithm is sampling for local exploration. So suppose X is a instance that we want to explain, and X dash is the interpretable feature space for that X. Then what they do is they create a locality of n number of instances. N is the given parameter, where what they do is, uh, to like from X, they create set of n other instances, and on these n instances, they train a explanation model using actual predictions of using actual prediction as label for this explanation model. So how they create this n number of instances is to create each instance, they take non-zero feature values from this x dash, which is interpretable representation of x, then recover if we call these non-zero feature values as z, then recover z in original representation, like say there are d features, then they recover that in the original representation, then they compute the actual prediction using the actual model that we want to whose prediction we want to explain, and use them as a label for explanation model. And then they train that explanation model, minimizing the locality aware loss plus model complexity, the function we saw in the earlier slide. So what is locality aware loss is, it's um, so f of z is the actual prediction of the complex model that we want to explain, and z dash is a interpretable feature representation of z, and we apply the explanation model and compute the uh, label that has been produced by explanation model. And then the difference, this is like a square loss, and we weight them using a similarity kernel. So what does that mean is, so we are producing these n number of instances from x, and we compute how similar that particular instance is to x. So we just weight this loss function with this similarity measure. So more similarities, for that loss should be very minimal. We can bear more loss for less similar instance.
So if the so x prime here can also be x, right? So for example, if it is AR prediction where the features are probably directly interpretable as it is, we don't need the separate interpretable feature space,
Yeah.
then x prime can be x also.
Yes. Yes. It can be
Okay.
excel.
So the line algorithm decides the x prime, or who decides?
It does it decides on its own.
Okay, so if you have trained on embeddings,
Mm-hmm.
then x. So what will be x prime there?
There, like we earlier defined, it
Yeah,
will
so
be,
it will be the bag of words.
yeah. In case of text classification, it's like bag of word. In case of like AR prediction is numerical one, so I don't think they will replace that with interpretable feature space.
Okay, okay, yeah. So only when it is
Image or
needed, they
text.
might replace.
Yeah.
Okay, yeah.
Yeah. So the algorithm is like this. So we have a classifier that whose prediction we want to explain. Then number of samples, that is the locality. It defines the locality of number of instances on which we want to train the explanation model. Then the instance that we want to explain, its interpretable version x dash, and then similarity kernel. The similarity kernel can be, in case of text classification, they use cosine similarity, and in case of image, they use Euclidean distance. Um, and length of explanation,
What do
like
you use
how
for
much
image?
Euclidean distance.
Euclidean distance. Okay, okay.
And this is the length of explanation that we want, like how many number of features we want in the explanation. So initially, Z is the locality. So we just n number of times we sample around x dash to get local similar instance to x dash, and then append it to z. We do this n number of times to get n number of instances in similar instances on which we can train the explanation model. And then they use least square methods. First of all, out of all the features, they need to find out, as we want only k features in the explanation, they need to find out uh, which k features they should use for training the explanation model. So there they use um, lasso regression to detect those important features, and use least square methods to fit a linear model and return the weights of the features. Um, so these weights of the feature are kind of explanation of the for that particular instance. Now we will see an example. So suppose this is a complex model boundary like this, and this is this red cross, bold red cross is suppose the instance that we want to explain. So what the line will do is it will produce these locality of instances, and then will fit a linear model, and we'll try to explain on the basis of that. So one of the usage they have highlighted is, let's say we have trained two algorithms on news corpus, where the task was to predict whether the news is atheism related or Christianian related. So first algorithm has both of them has predicted atheism. Prediction is correct, but first algorithm says God was important word. God and forest was important word, and that's why it predicted it as atheism. Whereas second algorithm said hosting, host, RE, and NNTP are the words that contributed to atheism class. So from here, if at all the algorithm to accuracy is very high, we should not use it. So uh, that's how it can help. Then like suppose, so now we can use line to explain each instance, but we may not have the time to go through all the instances to come to find out an explanation for the model, global explanation for the model. So can we take out only n number of explanations from all the explanation which will globally explain the model? So they have one algorithm which they call it as submodular peak for explaining the model, which tries to extract an important explanation which can explain the model globally. N is the parameter to their algorithm.
So this can be used for even our um,
AR,
missile thing, right?
um,
Possibly.
yeah,
If because it's explaining it globally.
yeah, it is explaining the model, but
Yeah,
we wanted to have explanation for buckets.
yeah. So if we but the data that it is taking sampling is from, suppose we restrict that to the bucket,
Yeah. So
then
like they have trained, what they do is they train classifier using actual prediction by the model as label, and that's what we are doing is we are taking bucket as a label. So I think we are doing similar thing to extract the explanations for bucket.
okay.
Only thing is we are using this decision tree or correlation based.
Right. And also, I was thinking that instead of line generating those samples, right,
Yeah,
neighborhood samples,
yeah,
if we provide those bucket samples,
yeah,
then it is almost as if it is the explanation of the bucket.
yeah,
That also, if there is a way of kind of passing that samples that it generates instead of Lime itself creating, then this might work.
yeah.
Okay.
Sorry, that. So what is this submodular peak algorithm is? Suppose we have these five instances and five features. So now, first of all, it tries to explain this first instance, and with the explanation, we have feature importances. So for the first instance, feature one and feature two was important. For second one, feature two and feature three was important, and so on. So from here, we can observe feature two is the most important feature. And if we take only fifth instance and second instance, we can cover most of them, most of the features. Yeah, so this is how they do it. They try in the greedy way, they try to find out instances which can cover maximum number of features, which is again a parameter to the algorithm, like how many features we want. And yeah, so in this case, they have selected second and fifth instance as an explanation to explain the model globally. Mm, So we will go through some demo. Here they are considering 120 newsgroup data set and considering atheism and Christian as a label or as a class. And then they are just using TF-IDF vectorizer to compute the features. So we have some train vectors and test vectors. And then they are training the random forest classifier. Um, so F1 score of random forest classifier is 92%. Now they are trying to explain the predictions using line. So here we have instantiated the line text explainer. Now suppose we take out some document, it is third document. The probability of Christianity is 0.414 and true class is atheism. So and classifier got these feature importances. The explanation got these feature importances, the line explanations. If we visualize them, then the explanation for class Christianity is so as posting and host and NNTP and all are occurring in that, that's why the class should be atheism and not the Christianity. Then so we will see SP line demo on the same news group data set. So here they just instance call the submodular peak. And here we have mentioned we want only two explanations as a model explanation. So these two explanations we get in the output. So what they are saying in atheism, mostly in Bill writes an article and God is the word that contributes to atheism. And in Christianity, in should not be present. God, church, the, in, church are the words which contribute to Christianity. So yeah, that was for images.
So that was the global explanation, is it?
Yeah, it was a global explanation, and we can mention how many uh, explanation we want in the output
So this
to.
submodular pick should be enough for our um, explanations or what? For the decile.
Actually, it's like explaining the model, but we want decile level explanations.
Uh, yeah, no, but if you train the, let's say, random forest over the decile classes,
Yeah,
then it will, so this will it give the explanation for each decile class?
yeah, it will give. Yeah,
Maybe we should try that, and then it might be,
yeah, yeah, it will give. And there is one Microsoft PySpark Lime implementation as well
yeah,
in
but maybe
Python.
first we can just try in Python.
Yeah,
Uh, with that deciles as labels, if we just train a random forest here and then get this submodular thing, it might be insightful.
yeah, yeah.
Okay.
And for images, so suppose this is the image. They have used Inception Net, pre-trained model of Inception Net. So this is classified as American black deer. So if we try to explain that model, then this is the part of image which model has used to detect it as a American black uh, deer. So
But this is just a random patch, right? It is trying lots of random patches and one gave the maximum.
what line does is for interpretable representation. So suppose we have 5 images. For each of those 5 images, it using some standard algorithms of image processing, it tries to extract continuous feature groups. Like say this is one contiguous feature group, which
Yeah.
is grass. Here also contiguous feature groups, and each of the image, these contiguous feature groups will be different. Now this is like a dictionary, like we have in the natural language processing
Hmm.
of words, continuous group of pixel dictionary. Now suppose we have 120 such contiguous group of pixel which are distinct. Now for each image, they will form a binary vector where they will specify that in this image, out of these 120, these 5 are present and all others are absent. And on that presentation representation, they will train a linear model.
Okay. But if this was, let's say, a multicolored cat, right? Golden, white, black, whatever.
Yeah, so then it will have been difficult to explain.
Yeah, maybe. Yeah, then okay. It
But
would be
that
interesting. Yeah.
Yeah, but in the data set, suppose there are multiple such images of multicolor cats,
Hmm.
then it would have those continuous group of pixels of different colors
Okay.
for, for those images, and I think it will be able to detect.
It will still be able to produce a region like this.
Yeah, maybe means we will have to
Okay.
try.
Okay.
But here at least it looks very promising.
Yeah. Yeah.
That's all. About.
Okay. Thanks, Deepavesh. Anybody has any questions? Yeah, so I think that submodular pick might be worth trying for the deciles, where
Yeah,
the classifier is built with the decile ID as the label.
yeah.
The other thing is that whether we can replace the lime sampling by just telling it to sample from the deciles themselves.
Yeah,
Uh, Yeah, so those are the two things I can think of. Okay, no other questions, then we can conclude and go to the update.